Hello, our viewers. Previously on our discussion in angular motion, we have tried to solve this problem at last. So on that problem, it was a question about a torque or moment of force. So we have tried to determine the moment of force exerted at this point due to the weight of or the mass of this object. And there is also a torque exerted due to the weight of the bar itself. Previously we have mentioned that the bar itself has a mass of 4 kilogram. So it's possible to find the net moment of force or torque by using or determining both torques due to the weight of the bar and due to the weight of the load. Therefore, let's try to solve that and finalize the previous concept. So in this case, our bar is pivoted here, and the weights of a given load, which is 10 kilogram, the weight is equals to mass times gravity, which is 100 Newton. 100 Newton, the mass is 10 kilogram, and the acceleration due to gravity is 10, so it's 100 Newton. So we have determined the torque, the moment of force exerted due to this weight. And the other concept here is there is a moment of force exerted clockwise due to the weight of the bar itself. The weight of the bar, the mass of the bar is 4 kilogram, so mass times gravity gives us the weight. Therefore, 4 times 10 gives us 40 Newton. So the distance from this to this was 4 meter. And for regular bodies, for uniform bodies, the center of mass or the weight is found exactly at the geometrical center. Therefore, it is 2 meters. This is our pivotal point. We'll try to see this under the concept of equilibrium actually, but here to determine the net moment of force or torque, we should have to add these two concepts. First, the torque due to the weight of the bar, and the torque due to the weight of the load. Here you have a load, okay? And here we have the weight of the bar. Therefore, the angle between the moment arm and the force or the weight is 53 degree. Again, previously you have also found this to be 53 degree. Therefore, it's possible to determine the torque or the moment of force due to the weight as torque tau is equals to force times r times sine theta. The force is all due to the weight of the bar, and the weight of the bar is 40 Newton, and the distance or the moment arm, we call it to be moment arm, from the pivot to the weight is 2 meter. And sine theta, where theta is the angle between the moment arm and the weight, and it is 53. So sine 53 is 0.8. Therefore, it's possible to find this to be 18 times 0.8 gives us 64 Newton meter. 64 Newton meter acting clockwise. And previously we have also found the moments of force or the torque due to the load to be 320 Newton. I hope you remember this. 320 Newton meter clockwise. So therefore, the net torque or the net moment of force should be added because 320 Newton meter acting clockwise, again 64 Newton meter clockwise. Both are acting clockwise, so we can add and find the net moment of force. But if there is a counterclockwise torque, we should have to subtract one the other. Therefore, in our previous question, it asks us to determine the net torque, the net moment of force. Therefore, we should have to add these two, 320 Newton meter clockwise plus 64 Newton meter clockwise again. Therefore, we should have to add these two all together and find 364 Newton meter clockwise. Both are acting clockwise direction. And there is a sign convention to use negative for clockwise. It's possible to say negative 364 Newton meter. If you put your answer like this, it means that it's acting toward this clockwise. Conventionally, negative torque means clockwise. So this was what we have seen previously. Now let's proceed on the other subtopics. So the next subtopic is we need to compare the dynamics concepts, translational dynamics and rotational dynamics. Under translational dynamics, the very important concept is in translational dynamics, suppose if you have a box here, as this box is translated and moving around here, at some point here, the net force exerted on this object, the net force exerted on this object is given as mass times acceleration. This is the basic concept in dynamics, in translational as well as in rotational dynamics. So in translational dynamics, from Newton's second law, or law of acceleration, states that whenever there is a net force exerted on a given object, that object will accelerate. So that net force is given as mass times acceleration, and the net force might appear due to a different agents, different forms of force exerted here. It might be the gravitational, it might be frictional, it might be applied external force, and so on. So the net force, if the net force is zero, there is no acceleration. The object is rather moving with a constant velocity, or the object is at rest. That is Newton's first law concept. The second law states that if the net force is different from zero, therefore the object is accelerating. So we have to have a similar concept for rotating object, for rotational object. So let's see for rotational objects here. Under translational dynamics, net force is mass times acceleration. How about for rotating object? If something is rotating, then how do we determine this concept? Okay, so to determine this concept, we can have a rotating object here. Here you have the axis. And if you exert, if this is the net force exerted on this massive body, and the force is found at a distance of r, from the center of the axis. Therefore, from the law of dynamics, it states that net force is equals to mass times acceleration. If we multiply both sides by r, net force times r gives us mass times acceleration times r. We have to multiply with r in both directions. Therefore, the net force times r is already defined as net torque. We know that it is torque, okay? Net torque. And the other expression is, we know that acceleration can be represented using rotational acceleration, alpha, as acceleration A can be given as r times alpha, where alpha is angular acceleration. Therefore, when you substitute here, mass times, instead of translational acceleration or tangential acceleration, it's possible to have r times alpha, and here you have r again. When you multiply these two, mr squared alpha. Okay, what does it mean by mass times r squared? Well, it is known to be moment of inertia, I times alpha. Therefore, net torque for rotating objects is given as I times alpha. For a translational body, net force is given as mass times acceleration. And the analogy or analogous translation of, or the similarity expression of this for rotating bodies, for force, the analogous concept is torque, net torque. Okay, for mass, rotational body, for rotating body is termed as moment of inertia. For acceleration, we should have to have a correspondent acceleration, angular acceleration. Therefore, this is for translational rotational body, whereas this is for translational or linear body, when objects are moving linearly. we should have to use this equation. When objects are rotating, we should have to use this dynamics concept. Okay, so let's try to see this. This is for translational body, for rotational body, sorry. This is for rotational body, whereas this is for translational body. Now let's try to see how to apply those equations in problems. That is the basic concept. Look at it here. You have learned in Unit 4, the concept of dynamics, a translational or a linear dynamics. You are familiar with such problems. Okay? In that problems, for only translational concept, you just ignore the mass of this pulley and the frictionless as well as massless pulley. You have been using this. But in rotational motion, you should have to consider the mass of these rotating objects or the pulley. Therefore, that is the difference. In this case, it's purely translational, which is a linear. This object is moving linearly. This object is moving linearly. We don't consider the rotational effect of the pulley, massless pulley. But here, there is a translational movement of these two. These two objects are moving linearly. Mass 1 and mass 2 are moving linearly, whereas the pulley is rotating. Therefore, we should have to apply a law of dynamics for these two, translational dynamics, but for this one, we should have to use rotational dynamics. Let's try to solve this. For example, in this case, it's possible to find the acceleration of this system. You might release this object so that this object is moving downward. So what is the net acceleration of this object? If the net force is 0, this object is considered to be in equilibrium. We'll try to see this in next unit. But now it's moving. While this object is moving downward, this object is moving to the right, and the pulley is rotating. Therefore, we should have to have the free body diagrams of each bodies. Okay? Here we have mass 1, mass 2, and as well as the pulley. Always try to solve such problems. First, you have to consider what is the initial force exerting on these bodies. What is the triggering force? The force that initiates this motion is the gravitational force. Okay? The gravitational force exerted on this mass 1, is m1g, the weight of mass 1. When m1g is exerted downward, this force, the force exerted on the string, is known to be tension. The tension tries to react oppositely. So we should have to consider these two cases. The tension has two cases. One, for this mass, it is oppositely reacting. When m1g is acting downward, the tension 1 is acting oppositely upward, reacting oppositely. And in this case, for the pulley, the same tension is acting to rotate clockwise. Therefore, here, m1g is acting downward, and the tension T1 is acting upward. And again, for the pulley, tension 1 tends to rotate it clockwise. And again, while it moves clockwise, look at here on this tension. While it moves clockwise, the tension exerted on this part, on this segment, try to act oppositely. So in this case, it is acting to the left. Okay? And again, these bodies or these objects are moving as a system. Due to that, the force exerted on this tension T, So when this tension is exerted on mass 2, it will move to the right. Actually, if there is a frictional force, you can add here frictional force. If there is a frictional force, but here it says frictionless, so that we can neglect friction. Okay, frictional force is 0. Therefore, what are the force components exerted on each segment? This is known to be the free body diagram. You should have to put the free body diagrams of each mass separately so that you can find equation. This is for translational case. whereas this is for rotational case. So above we have found that there is mass 1. The force exerted on mass 1 is m1g. m1g is acting downward. The force exerted on mass 1 oppositely is tension T1. Tension T1. The other mass is the mass 2. Mass 2. Mass 2 is acting, the tension 2 is acting to the right, but there is no frictional force here. The frictional force is actually 0. If there is frictional force, you can add that. As well as there are force acting downward, which is the weight of the object, m2g. Usually m2g are used whenever there is a frictional force. It's very helpful to determine the normal force. I hope you have learned this in dynamics concept. And the other concept is for rotational body, for the disk or for the pulley. Pulley is usually disk, so we can use that. Here, the pulley is tending to rotate clockwise due to the tension exerted here. And it tends to rotate counterclockwise or anti-clockwise due to the tension exerted to the right, to this direction. In both cases, here we have the axis of rotation. We have the axis, and here we have the radius of the pulley. We have the radius of the pulley. Therefore, for these two bodies, we should have to write the linear dynamics equation. For this one, we should have to write the rotational dynamics equation. Then solve it all together. Now let's see. When you apply a linear dynamics here, net force is equal to mass times acceleration. That is a linear or a translational dynamics. But for this one, the net torque is I times alpha. I times alpha. Therefore, let's try to put those equations, those forces. What are the net force exerted on this mass? Well, the net force are, one, the weight due to, the force due to the weight of the object. The weight of the object. In this case, mass 1 is 6 kilogram. 6 times 10 gives us 16 Newton. 16 Newton is the force exerted downward on mass 1. And the other force is tension T1. Therefore, when you put this, the net force on mass 1 times A, m1g is acting downward, tension T1 is acting upward, m1A. This is your first equation. The second equation for mass 2, when you apply translational dynamics, it gives us net force is equal to m2A. m2A. So tension T2, which is acting in this direction, minus frictional force is equal to m2A. But in this case, there is no frictional force. The frictional force is already 0. So the tension 2 becomes m2A. We have our second equation. So far, these two are translational equations or translational dynamics. But here we have a rotational dynamics. And rotational dynamics state that net torque is equal to I times alpha, where I is the moment of inertia, alpha is the angular acceleration. And how do we determine the net torque? We know that torque tau is force F times R. Force F times R. In this case, torque tau, to determine the net torque tau, is equal to net force times R. What is the net force exerted on this rotating pulley, on this disk? The net force is all due to the tension exerted here. There is a tension which is acting clockwise, and there is a tension T2 which is acting anti-clockwise, tends to rotate this anti-clockwise. Therefore, the torque exerted due to tension 1, let it be T1, can be given as tau 1, tension T1 times R times sine theta. Usually theta in this case is 90. Look at here, this is the axis. Let's make it like this. Here we have the radius R, and here we have the tension T. The angle is 90. Therefore, it's possible to use T1 times R times sine 90 gives us 1. Therefore, tension exerted, the torque exerted due to tension 1 is T1 times R. T1 times R. Whereas the tension T2 acts counterclockwise. From the axis to here is again radius R. So the angle here is 90. Again, the tension T2 exerts counterclockwise torque. Tau 2 is equal to tension T2 times R times sine theta, and theta is 90 degree. So sine 90 is 1, therefore it's possible to have a torque which is acting counterclockwise. When you add these two, clockwise and counterclockwise, you can have T1R. Let's take it here. T1R, the tension which is acting clockwise, minus the tension T2R, we can subtract these two, is equals to I times alpha. This is how we determine the net torque or moment of force. T1 minus T2. T1 is acting clockwise, and this one is counterclockwise, times R, gives us I times alpha. What do you mean by alpha? We know that alpha is angular acceleration. It is related with that of a linear or translational acceleration as A is equals to R times alpha. From this, alpha or angular acceleration is linear acceleration over radius R. And moment of inertia is given as mr squared, mr squared. Therefore, when you substitute here, you have, we can cancel out R. Here we have R. We can eliminate R. These are cancelled out. And we have the difference tension 1 minus tension 2 is equals to mass times acceleration. What is this mass? This mass is the mass of the pulley. Okay? This is the mass of the pulley. This acceleration is the acceleration of a system. In this case, m2a only for tension mass 2. And here we have such an equation. Therefore, we should have to equate these three equations. You have to sum all these three equations because they are acting as a system. You just find the free body diagram. This is known as FBD, free body diagram. Freely, you can find the net force on each components. Here you have two mass and a pulley as well. Then you have to add all these equations all together. Therefore, from the first one, we have m1g minus tension T1 is equals to m1a. From the second mass, we have T2 is equals to m2a. And from the pulley, from the rotational dynamics, T1 minus T2 is equals to m2a. Now look at here, m1g minus T1, negative T1 or minus T1 can be cancelled out with T1. Whenever you add these two, negative plus positive is 0, negative plus positive is 0. So we can cancel. This is negative, you can cancel with this one. This is negative, this is positive, you can cancel this one. When you add this, the only quantity left here is m1g. Okay? And on this case, you have m1a, m times a, m2a. In this case, this is mass 1, this is mass of the disk or the pulley, m2a. Therefore, we can add all these two, m1 plus mass of the pulley plus m2, the whole times acceleration a. This is how we determine the net acceleration. It's also possible to determine the tension. Each tension is possible to find tension 1, it's possible to find tension 2, and so on. So in this case, from the above question, we have the mass here. Here we have mass 6 kilogram, here we have 4 kilogram, and the mass of the pulley is 2 kilogram. We can determine the acceleration. Therefore, when you substitute all the numbers, you can find acceleration. Acceleration A as 5 meter per second squared. 5 meter per second squared. So this is how we solve rotational dynamics. Actually, it's a mixed dynamics, both translational and rotational dynamics. And this is commonly, redundantly, appears in your national exam. Therefore, you should have to solve for such problems. You should have to have a skill, and you should have to develop a skill of solving such problems, and you can find a lot of problems, such problems, on your textbooks and as well as on different physics books. Now let's proceed. The next concept is, so far we have tried to see the rotational kinematics and rotational dynamics. Now let's try to see rotational work, energy, and power concepts. Rotational work, energy, and power concept. In our previous discussion, we have discussed about a linear work, energy, and power concept in Unit 5. And here we can parallelly see for rotational work, energy, and power. In linear motion, work is given as force times displacement. The analogous concept of force in rotating objects, or the similarity, mean for force we can have torque, and for displacement S we can have theta. Okay, we can have theta. We know that from the torque concept, tau is F times R, F times R, okay? And from a displacement concept, we know that displacement can be given as R times theta. So in this case, what do you mean by force? Well, force F is net torque tau over R, Therefore, when you substitute here for rotating body, we can have this equation. Work is equals to, instead of force, you can have torque over R. Okay? Instead of displacement, a linear displacement, you can have R times theta. So when you eliminate R, you can find that work is equals to torque tau times theta. The other concepts is energy. We have seen different forms of energy, potential energy, kinetic energy. We have also classified potential energy into elastic as well as gravitational and so on. But here, we just only focus on kinetic energy, energy due to motion or velocity. In translational kinematics, in translational motion, we have said that kinetic energy is equals to 1 over 2 mv squared, So in the same way, we can possibly find for kinetic energy for rotating object, as what? We know that kinetic energy is equals to half mv squared, But v, which is a translational velocity or a linear velocity, v can be given as r times omega when you correlate it with that of rotational angular velocity. Angular velocity times r gives us linear velocity. So when you substitute here, you can have 1 over 2 m instead of a linear velocity, r times omega, the whole squared. And this gives us 1 over 2 m r squared omega squared. 1 over 2 m times r squared, and here we have omega squared. What do you mean by mr squared? Students, I hope you have learned this one. We have already discussed. M times r squared gives us moment of inertia. So we can have the kinetic energy as 1 over 2 I omega squared. So that's the kinetic energy is already given us what? 1 over 2, the moment of inertia I, angular velocity squared. This is how we determine. And the other point is power. Power can be given as F times V, the force times V. This is instantaneous power actually, and it can be parallelly given for rotational body as torque tau times angular velocity V. Then let's proceed again. We have also a work energy theorem that we have already previously seen in Unit 5. So that work is equals to the net change of kinetic energy final. The same way, for rotating body, it's possible to have 1 over 2 I times omega final squared minus I times omega initial squared. This is known to be work energy theorem for rotational body. Now let's proceed for the other concepts. Here we have rolling motion or rolling of objects of rigid bodies. Here you have rigid bodies. These bodies might be rolling. So far, we have tried to see about a pure rotational motion. That means a motion of a given object, rotational motion of a given object at a fixed axis. And the center of mass has no velocity. In such case, we call it to be pure rotational motion. Pure rotational motion has center of mass with zero velocity, has no velocity. Center of mass has zero velocity. Look at here. And it has a fixed axis. The axis is through this, and this object is tending to rotate. Okay? When it comes out of rolling motion, the object itself is moving. And the center of mass itself has a velocity v, a translational velocity v. This object is tending to rotate and rotate like this, and as well as the center of mass has a velocity v, a translational velocity v. The center of mass has a translational velocity v, and the other objects has velocity, rotational velocity, and translational or tangential velocity. Therefore, this is known as rolling. This is known as pure rotational motion, and this is known as rolling motion. For rolling motion, suppose here you have center of mass exactly at the center. The velocity of these points at the rim. We have different points actually. There are different points. And here we have points here. Suppose if you have the axis here at this point, and if the velocity of this point is 0, let's take that the velocity of this point to be 0. And if you have the axis through here, and the center of mass has a velocity v of center of mass, if you have the velocity of center of mass, the velocity of a particle, let it be p prime, at the rim is twice of the velocity of center of mass. Here we have the velocity of center of mass, and at this point we can have twice of the velocity of the center of mass. So for rolling objects, the total kinetic energy, how do we determine the total kinetic energy for rolling bodies? The total kinetic energy can be determined using the summation of a translational, as we have previously seen. There is a translational for the center of mass, and there is also rotational for the other particles. Therefore, it is a summation of the total kinetic energy is the summation of translational kinetic energy and rotational kinetic energy. Total kinetic energy, translational as well as rotational. What is the translational kinetic energy? Translational kinetic energy is given as half mv squared. Half times the mass, center of mass of the rolling body. This is the rolling body. And it has center of mass. All the mass are actually concentrated here. And it has a velocity v. Therefore, half mv squared is the translational kinetic energy. And every particles rotate. There are rotational motion. Therefore, for rotational kinetic energy, 1/2 I omega squared. So this is how we determine the total kinetic energy. This is total kinetic energy, half times mass, the moment of inertia I over r squared times v squared. How did find v squared? Because that angular velocity omega is linear velocity over r. So when you substitute here, you can find such an expression. This is how we determine the total kinetic energy. Now, students, let me ask you one very important question. How do we determine the velocity of given objects, rolling objects, as they move across or around on an inclined plane? On an inclined plane. Suppose here you have inclined plane, and let's try to determine the velocity as they reach at the bottom. So this is all for today. For next period, please try to determine which objects. Let's have 3 objects here. We have a ring, cylinder, and a sphere. Which objects reach at the bottom first? Just put your answer precedently, one in the other. First one, the second one, and the third one. So which objects reach at the bottom? Suppose that all the objects have the same mass, their mass is the same, and they all have the same radius. All their radius remains the same, r. So what would be, which object reaches first at the bottom and which object reaches last at the bottom? We'll try to see this next time. So bye-bye for today.